Now that we've been introduced to work, kinetic energy, potential energies, and thermal energy, we can focus on the entire principle of energy conversions, transfers, and transformations. And we write it, being very explicit, to say that the external work, or the work done by the environment on a system, is going to cause a change in its kinetic energy or a change in any potential energies. This could be gravity, it could be spring, so there may be both. You could have two different terms of potential energy, but I'll just do delta U, but know that it could be different forms of potential energy. And then the possibility of an increase in thermal energy. Reemphasizing that thermal energy, we don't do E thermal initial and E thermal final because that's a molecular picture. And so we focus on just increases due to friction. And so this is like one number, whereas these two are a difference between two numbers. So K initial, K final minus K initial, U final minus U initial. Okay, and this specifies that this is the system. Okay, the system, and this is the environment. And it is possible for the system to do work on the environment, or in other words, when we do all our calculations, this ends up being negative. Okay, so we're going to focus on a case where we simply call it conservation of mechanical energy. And what we say is if we pick our system to be such that there is no external work done, okay, so no forces over a distance from the environment on our system, and we also say that there are no dissipative forces inside the system, so no friction, basically, then we have just kinetic energy and potential energy that have the option of transforming one into the other. So one of the most effective ways of writing this is separating out with the final minus initials, collecting the initials together, and collecting the finals together, giving us K initial plus U initial equals K final plus U final. So this is conservation of mechanical energy. Again, under those two assumptions, that there is no external work done on the system and there are no dissipative forces internal to the system. Okay. Now this allows us to solve actually a lot of different problems. There's a lot of situations where our system can be chosen such that this is sufficient, and it's super powerful because I don't care about processes. I just care about what it starts with and what it ends with. That's the beauty of thinking about energy, which we'll find a little bit later. That's not true for all systems, or like that. I should say many systems in nature don't obey this, and so we have to do a more careful approach. But there are many of daily life situations where this does apply. The conservation of mechanical energy for an isolated system that has no dissipative forces inside